Okay, section 3.5, Bernoulli Trials. This section introduces a formula to kind of some of the work that we've been focusing on. But before we get to the formula, I kind of want to talk a little bit just about what Bernoulli trials are and sort of how the formula comes about. Like why does the formula work the way it does? All right. But a Bernoulli trial, just to keep it plain and simple, is focused on only two possible outcomes and the probability of each of those outcomes. So normally we call these outcomes a success or failure. So think of an example like if you're taking a multiple choice test, right? For any particular question, you have either two outcomes: probability of success, where you get the question right, or the probability of failure, where you get the question wrong. So you're either going to get the question right or the question wrong, and then there's a probability associated to that. Probability of getting it right, if it's got four choices, is 1 out of 4. The probability of getting it wrong is 3 out of 4. So that information will be used in the formula when we get to it. But Bernoulli trials are always focused on kind of having those two outcomes, a success or failure. So let's look at this first example. Suppose an experiment consists of 2 repetitions of a Bernoulli trial with the probability of success equal to 1/3 and the probability of failure equal to 2/3. What is the probability that exactly one success is obtained in the 2 trials? So we're going to start kind of slow and use a tree diagram here to sort of, kind of slowly introduce ourselves to Bernoulli trials. So my first event, or my first trial, right? It's either a success or a failure. Now the probability of success is 1/3, right? The probability of failure is 2/3. And on my second go, because there's 2 repetitions of success or failure, success is still 1/3, failure is still 2/3, right? So what is the probability that exactly one success is obtained in the 2 trials? So let's focus on the one success part of this. Now, if we follow the branches, that's a success and that's a success there. That's 2 successes. So I'm not really going to concern myself with that probability for the moment. Success and failure, that's probability of that's 1 success right there. So the probability of that would be those 2 branches, 1/3 times 2/3, which equals 2/9. All right, and then if we fail, then succeed, that's another 1 success. So that would be 2/3 times 1/3, which equals 2/9 again. So the probability of getting exactly 1 success is 2/9 plus 2/9, right? We just add these 2 probabilities together, 2/9 plus 2/9, which equals 4/9. So there's your probability of exactly 1 success. So that's more of a review of kind of what we've talked about in previous sections. All right, this is a Bernoulli trial, though, because it's broken into only success or failure. There's only 2 possible outcomes here. All right, we'll come back to that example later when we have the formula to see how the formula works with that. Now, that was very simple, so it might kind of be easier to do without the formula. But in a lot of cases, we could have success and failures of not just 2 trials like we saw there, but of like 50 trials, something ridiculous. And drawing a tree diagram for that would be absolutely absurd. So the formula will definitely come in handy when we get to more complicated, more elaborate type of examples. All right. But example 2 kind of illustrates what the formula is going to eventually be. So we're looking at an experiment consisting of 4 trials. All right. Again, Bernoulli trials means that each trial is just broken down to either success or failure. Compute the probabilities of obtaining exactly R successes. And we're going to do this for each type of success, whether we have 0 successes, 1, 2, 3, or all 4 successes. We're going to find the probability of every single one of them. Okay, and we're going to use a tree diagram here, although it's a very elaborate tree diagram. It's going to at least show us by the outcomes, what kind of the formula eventually starts to be, how the formula kind of works the way it does. So I'm going to go ahead and skip ahead here. I've got the tree diagram already made, right? You can see it's 4 trials, and each trial is success or failure, right? So, oops, too far. So now if you follow each branch, you'll see the outcomes that I've listed over here on the right-hand side. Now, success, 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 all 4 successes, and I'm relabeling them basically P for a successful probability, and Q will be for a failed attempt, a failed probability. Okay, so 4 successes, 4 P's. If I follow the branches success, 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 and then failure, right? Success, 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 failure, then I have P, 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 Q, right? 3 successful probabilities, 1 failed probability. Now, the reason I'm using P and Q is because we're going to use P and Q in our formula. So it'll make sense when we get to that. So P will be for successful probabilities, Q will be for failed probabilities. And so I've done that for each of these branches. Success, success, failure, success is P, P, Q, P, right? So, and you could trace these along, and like I said, I've already filled it out, so I'm not going to just repeat it for you. But you'll see that for each branch, failure, success, 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 I've gone ahead and noted the 4 outcomes, whether it failed to success, and then translated into Q and P. Okay. Now, the big thing I want to point out is what the similarities are between all of these P and Qs. All right. So this is all 4 successes, all 4 P. So again, this is P to the 4th power. This one has 3 P's and 1 Q. That's 3 successes, so P to the 3rd power, and then 1 Q. This one here, notice it's also got 3 successes and 1 failure, so it is also P to the 3rd power, and then Q. And that one down there is 2 P's, 2 Q's, so P to the 2nd, Q to the 2nd. Okay. Now, I can't write small enough to kind of fit all of these, but you got to get the idea, right? Here you've got 2 P's and 2 Q's, so that's P to the 2nd, Q to the 2nd. Here you've got 1 P and then Q to the 3rd. Here you got 1 Q and P to the 3rd, right, and so on. So what we'll do is you can write all those out, and then you'll total it up, because there's multiple ones that have 3 P's and 1 Q. There are multiple ones that have 2 P's and 2 Q's. For example, if I circle all the ones that have 3 P's and 1 Q, let's see if I can find them all. 3 P's, 1 Q. Q, P, Q, P, Q, P, Q, 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 P, P, Q, Q, P, Q. I believe, I think it's just those, right? There are 4 P to the 3rds and Q to the 1sts, right? There's only one that's all P, right? There's only one that's all P to the 4th. How many of the P to the 2nds, Q to the 2nds can we find? So 2 P's, 2 Q's. So that would be here, 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 and there. So those are all the ones that have exactly 2 Q's and exactly 2 P's. So that is, count them up, 6, right? And if you want to find exactly how many have 1 P and 3 Q's, well, that would be, let's see, 1 P and 3 Q's. 1 P and 3 Q's. 1 P and 3 Q's, 1 P and 3 Q's. So there's 4 there. And then the only thing that we're missing is the one that has no P's and it's all 4 Q's. And there's only 1 in total, right? So there's sort of a pattern here that you can kind of see, 1, 4, 6, 4, 1. And that's going to explain a little bit for us. Let's see here. Let me erase that. Let me go ahead and click ahead. So I've written it down here. So the probability of 0 successes is straight 4 Qs. Probability of 1 success occurred 4 times. Probability of 2 successes appeared 6 times. Probability of 3 successes appeared 4 times. Probability of 4 successes appeared once as well. All right. Now that's going to look more familiar to us once we start using the formula, because the formula is going to be, let's see if it's on the next one. The formula is this. So we have a combination, n choosing r, p, which represents the probability of success to the r power of r power, times q to the n minus r power. Now, it looks kind of weird at first, but it's actually going to be super easy to use and super useful for us. So we don't have to draw ridiculous tree diagrams like that. So we're already familiar with combinations, which is good. We should be able to work those out. And actually, I'll show you in the calculator in class exactly how we can quickly compute that just using the calculators. And here it's just we're going to be plugging in values for P, Q, and N and R. All right. And you'll kind of see where how that last example sort of showed us. The 1, the 4, the 6s were all coming from the combination of, let's say, what do we have? We had 4, right? And if we wanted to choose 4 successes, let's say, so this is for all 4 successes, probability of 4 successes. We had 4 trials and all 4 were successes. Now the probability of success was unknown to us. We just called it P at the time. But R represents exactly the number of successes we had. So we had all 4 successes, and then Q represents the number of times we failed. We had none of those, right? Or you can think of it as N minus R. So again, that's 4 minus 4, which would be 0. So this comes out to 1 P to the 4th, Q to the 0, which is just 1 P to the 4th, which explains this right here, probability of 4 successes. If you wanted to see the probability of 3 successes, right, that'd be combination of 4 choosing 3 successes. We would have R is 3. Remember, this is N, this is R. R is 3 because we had 3 successes. Q is N minus R, which is 4 minus 3, which would be 1, right? So we had 4 trials, 3 of them were successes, 1 of them was a failure. And if you work this out, the combination of 4 choose 3 is 4. We would still have P to the 3rd, and we would still have Q to the 1st. And that would explain, go backwards. The probability of 3 successes here. 4 P to the 3rd Q. So the formula works, and it'll make sense for these as well. Now, normally we're going to know what P is and what Q is, and that's going to be important for us when we actually try to figure out the exact probability, whether it's 0.15 or whatever the probability is. But here it just kind of explains where the formula sort of originates from, sort of how it's formed. Okay, but remember that formula. We'll be writing it down. We'll be using it a lot. So let's try to use it back to example 1. So remember example 1? Go away. Example 1 had probability of success. We had 2 trials, right? If you go back and look at example 1, we had 2 trials. Probability of success was 1/3. Probability of failure was 2/3. So P is going to be 1/3 because that's P is for success, Q is for failure. And we're asked to find the probability of exactly 1 success. So if you use the formula to answer this, we would have the combination of 2 choosing 1 because we're doing 2 trials and we're looking for 1 exact success. So N in this case is 2, R in this case is 1. I've mentioned that here in the problem, right? Times P to the r power. So let me go ahead and let me rewrite the formula up here so you can see what I'm plugging in. P to the r q, oops, that's not a q, q to the n minus r. So I already know my combination n and r, 2 and 1. P, the probability is 1/3, because my probability of success is 1/3. R, how many successes am I looking for? R is 1. I'm looking for 1 success. Q, which is the probability of failure, is 2/3. And then I'm plugging in n minus r power. So n again was 2, because we have 2 trials, minus the 1 success. So 2 minus 1 goes there. Now I'm going to go ahead and simplify that. 2 minus 1 is 1. All right, so there's your formula, and we can work this out. We can try this and see if we get the same result we got in example 1. Example 1, if we go back, I believe was 4/9 was our answer. So let's see if the formula comes up and gives us 4/9. It should. So the combination of n choose r is, of 2 choosing 1, is just 2. Now multiply that with 1/3 to the first power. 1/3 to the first power is just 1/3. Times 2/3 to the first power, which is still 2/3. And when we multiply this together, remember 2 is the same as 2 over 1, if that helps. So 2 times 1 times 2 is 4. 1 times 3 times 3 is 9. So you get the probability of 4/9. So I don't need to draw a tree diagram. I can just use my formula. Okay. Everything should be given to us. All we really need to know is n, r, and p and q. And that should all be explained in the problem that we're given. So in example 3, a game of chance you play by rolling a fair die 4 times, and you count the number of results, which are sixes. I guess, okay, I was trying to say sixes here. I was wondering why I said 6s. And that's supposed to be a period, I suppose. So typos on my part. What is the probability that in one play of the game you obtain exactly 3 6s? All right. So here, let's try to establish, we know we're going to use our Bernoulli formula, P to the R, Q to the N minus R. Here we go. Let's try to figure out what N is, what R is, what P is, and what Q is. If I can figure out those things, then I'm just going to it's just plugging in, right? So N is how many trials I'm going to do. So I'm going to roll this die 4 times. So that's how many trials I have. So that's going to be my n value of 4. Now, how many successes am I looking for? I'm looking for exactly 3 successes. I'm rolling a 6 a success. And I want to know, if I roll the die 4 times, what's the probability that 3 of those times are 6s? So I'm looking for 3 successful rolls. Now, P, the probability of success. Now, when I roll a die, the probability of getting a success, because I'm looking for getting a 6, the probability of rolling a 6 is 1/6, right? So the probability of success is 1/6. That means the probability of failure is 5/6. So I have all the information I need. I'm going to plug into my formula, and we're going to see what I get as an answer. So I'm going to do the combination of n choosing r. N is 4 in this case. R is 3. Times the probability of success, which is 1/6, to the r power, r is 3, and then times q, probability of failure, which is 5/6, to the n minus r. So that's 4 minus 3. I'm going to go ahead and simplify that. 4 minus 3 is 1. So I'm just going to go ahead and write 1 up there. So there it is. Now let's just work it out. So let's do one piece at a time. The combination of 4 choosing 3 is 4. Okay, I'll let the calculator do that. If you really want to do it by hand, remember the combination formula is n factorial, n minus r factorial, r factorial. So you're more than welcome to use that formula to calculate it, but I think it'll be easier if you want to use the calculator. So 1/6 to the third power. If you want to use a calculator again, you can here, but just a heads up, when you have an exponent on a fraction like this, it really just means that you're taking 1 to the third power and 6 to the third power. So I'm going to go ahead and try and do that by hand. I know 1 to the third power is 1, and 6 to the third power, 6 times 6 times 6. I know you guys are superstitious and don't like that. It's 216, so it's 1 over 216. And now 6 to the first power is still just going to be 5 over 6, right? So remember, 4 is the same as 4 over 1 if you want to try multiplying this. So 4 times 1 times 5 is 20. And 6 times 216 is a big number. 1,296. So I'm willing to bet that both of these numbers are divisible by 4. So if I want to try and reduce it, let's see. It would be 5 over 324. Now, if you want to write that as decimal, be my guest. 5 divided by 324 is 0.015-ish. It's rounded, but it's about that. Okay, so let the formula do all the work here. You don't have to try too hard. You just have to let the calculator do most of the work. The formula is going to be super easy for us. We don't have to really think too much. We just need to know 4 values. You know, once we know those 4 values, it's just a matter of plugging in and playing around here. I didn't simplify my fraction in the problem, but I think you get the idea. All right, so solve the problem. Pose an example 2. Assume the probability of success is 1/4 and the probability of failure is 3/4. So remember example 2 had that big, what was that? The big table? Or the big tree diagram. So I'm going to go ahead and put all the math on here just to save time in the video, but I'll try to explain it the best I can when everything's there. So probability of 0 successes, right? You're using that formula again. You have 4 trials, and you have 0 successes. So you have n is 4, and r is 0. And now when you plug in p and q, you're plugging in p is 1/4 and q is 3/4. So you'll see me do that here, plugging in p and plugging in q. All right, now keep in mind that 0 is the exponent here because 0 is the r value. We're talking about 0 successes, and that means that the number of failures would be 4. So 0 successes, 4 failures, and when you do all the math, you do the combination. The combination comes out to be 1. This number goes away because it's to the 0 power, which is also 1. And 3/4 to the 4th power is 81 over 256. So we get 1 times 1 times that. We get 81 over 256 as the result. Right? So all of this is just basically just using the formula a lot. To try to find 1 success, you're using the same n value because you're still doing 4 trials, but r is 1 for 1 success. And when you work it all out, the combination of 4 choosing 1 is just going to be 4. You have the p-value, which is 1/4, again, remember, with 1 success, and the q-value, which is failure, 3 failures. Remember, 1 success, r is 1, n minus r is 3. So again, just let the calculator do all the calculating. I've shown you what each of these comes to. This number becomes 4. This number becomes 1/4 still, and 3/4 to the 3rd power becomes 27 over 64. So when you multiply all 3 of those quantities together, you get this simplified answer. So I'll leave it up there because I can explain this, but I'm just saying the same thing over and over again for all 5 of these. But I think it's interesting when you look at the probabilities, which of these kind of is the most likely and which one isn't. You know, it's very unlikely for this last one, 1 over 256. That's by far the smallest number here. And you would think that that would be unlikely because success is only 1/4. Basically, think of this as a multiple choice test, right, with 4 questions. And each question has 4 answer choices. And if you guessed on all 4 questions, just randomly, the probability that you would get all 4 of them right is only 1 out of 256. So very, very low. Unless you cheat, which is bad news, okay? How many examples are left? I kind of want to just hustle through this. Okay, only 2 more. Example 5. An NFL kicker knows that he makes 1/4 of his field goal attempts from more than 50 yards. He also knows that they are independent trials. In a certain game, he attempts 5 field goals of more than 50 yards. What is the probability he will make at least 2 of the 5 attempts? So there are 2 ways you can calculate this problem. You can find the probability of exactly 2 made, exactly 3 made, and exactly 4 made, and exactly 5 made, and add them all together. Because the question says, what's the probability he makes at least 2? So we have to find the probability he makes exactly 2, the probability he makes exactly 3, probability he makes exactly 4, or the probability he makes all 5 attempts. So that's doing the formula 4 separate times and then adding all the probabilities, all those results together, which could take a little bit of time, but if you want to practice the formula, you can certainly do it that way. The other way is find the probability that he makes none of the kicks and the probability he makes only one of the kicks. That's a fewer options, and then we can subtract that probability from the total. So this kicker is he's got 5 attempts to make a field goal, right? And we want to know what the probability is of he making at least 2 of the kicks. Not exactly 2, but at least 2. So if we were to do that, well, I guess this would be for 0 made, 1 made, 2 made, 3 made, 4 made, and all 5 made. We would have to find out the probability of exactly 2, add it with the probability of exactly 3, add it with the probability of exactly 4, and add it with the probability of exactly 5 to get a total here. Or, so that's option 1, like I was saying. Or we can find the probability of him making none and the probability of him making 1, and taking that as a difference between these. Because when you add up all of these, we know that the sum of them would always equal 1. So if I know what this is, right, then I'll know what's left over would be the probability he makes at least 2. So I'm going to go with the second option because it's only going to require me to use the formula twice rather than having me use the formula 4 times, and just do the difference. I think that'll be easier. So if he makes 0 out of the 5 attempts, so that's the combination, 5 attempts, successful at 0 of them. Now the probability of success is 1/4, right? So the p-value would be 1/4. And again, he's making 0 of them. Probability he fails then would have to be 3/4, and he would do that all 5 times. So there's your formula, and you can calculate it and work it all out. And I believe this would be 5 choosing 0 is just 1. This is also 1. And 3 to the 5th power over 4 to the 5th power is something very interesting. So 3 times. We have, that would be 243 over, what's 4 to the 5th power? 1024. I'm going to go ahead and get this number as a decimal, if that's okay. So 243 divided by 1024 is about 0.237. So I'm going to write that up here, 0.237. So that's a probability that he makes exactly none of the kicks, okay? So he's just a big time failure. I probably should have left that formula there because I could have just erased the numbers and plugged it back in. Let's find the probability that he makes exactly 1 successful kick. So that would be combination of 5 choosing 1. Probability of success is still 1/4, but now he's going to be successful 1 time, so 1/4 to the 1 power, times probability he fails, which is 3/4, and he would fail 4 times. So 1 success, 4 failures, and let's go ahead and calculate this. So this number would be 5. This number is 1/4. These are multiplication signs here. And then this would be 3 to the 4th power and 4 to the 4th power. So let me go ahead and do the calculation there. So 3 to the 4th power is 81. So let me just change this to 81. And 4 to the 4th power is 256. So the probability, 5 times 1 times 81, is, this number would be 405 on top, and then 1 times 4 times 256 is 1024. So again, I'm just going to write this as a decimal. So 405 divided by 1024 is 0.395. I'm just going to go ahead and round that to basically 0.4. So probability of him making exactly one kick is 0.4. So now, if I add these together, that's the probability that he either makes 0 or 1 kick. So that would be about 0.637. So if I subtract that from 1, then I have the probability that he makes at least 2 kicks or more. So 1 minus that would be, 0.363, I believe. So that's a little bit easier than doing, finding the probability of 2, 3, 4, and 5, and then adding all of them up.